Alright, a new video. I'm going to do section 5.3 the same way I'm going to do the next two sections, 5.4 and 5.5, which are about logarithmic functions, because they're very similar as they're inverses of each other. So before going over the functions themselves, I'm going to go over the properties of them. And instead of solving the equations that we have in each of the sections 5.3 and 5.4, we're going to skip those until we get to 5.6, where we're actually solving the problems. The reason I'm doing that is because we solve exponential and logarithmic functions by using each other because they're inverse functions. And each of the individual sections, they gloss over this fact and try to use the fact that the functions are one-to-one. So let's start with an exponential function. So let's start with an exponential function. Let's say we have f of x, and these are labeled because they have exponents. So I'm going to use 3 to the power of x. Now we can actually fairly easily prove that these are one-to-one. We'll start with the exponent properties. Now this should hopefully be review, but just for symmetry, I'm doing the properties of exponents, just like I'm going to do the properties of logarithms in the next video. So let's see, we've got a few of them. If I have a to the power of b times a to the power of c, this is multiplication among a common base of exponents. This works out to a to the b plus c. Now I'm going to skip the demonstrations of all of these because, well, either it should have already been done, but it's really just a product of the fact that exponents are repeated multiplication. I have b many a's and I have c many a's, and when I put them together I have b plus c many a's. Now what's often kind of skipped over is, since division is the opposite of multiplication, we use the opposite of addition. So if I have a to the power of b divided by a to the power of c, this is division among a common exponent. This will be a to the b minus c. And this can also be illustrated by using other facts. Division is the same thing as, multiplication by the reciprocal. And a reciprocal is something with a negative exponent, a to the minus c. So I've changed my multiplication into, I changed my division into a multiplication by utilizing a negative exponent. If I have a times b in parentheses to the power of c, then what do I get out of this? Well, the c exponents distribute across multiplication and division. So this is a to the c times b to the c. And likewise, if I have division, a over b to the power of c, division is just weird multiplication, so we distribute the same, a to the c over b to the c. Now something that's not true is we cannot distribute across addition. And then we'll have one final general property. So let's see, if I've got a to the b all raised to the power of c, exponents upon exponents, then what happens is I multiply the exponents together. Some less general but rather specific properties. If I raise something to the power of 1, that's just like multiplying by 1 actually, nothing changes. If I have a number and I raise it to the power of 0, then I get 1 as an answer. But we should note here that a should be not equal to 0. Generally speaking, when we're dealing with exponents, we try to stick with positive numbers, but negative numbers are an option. But if you're dealing with negative numbers, you really can't use exponents that aren't integers, because as far as talking about functions, you get really, really bad domain problems if you try to use negative numbers for the base. So with all that out of the way, an exponential function is any function of the form we say f of x equals c a to the power of x. So here c is a constant, a is the base of the exponential expression, and x is the variable exponent. Now, you could try to generalize this a little bit. So, like, I could try g of x equals, I don't know, 3 to the 4x minus 7. But what happens is, from properties of exponents, this is 3 to the minus 7 times 3 to the 4x. So I've also rearranged it, but I'm using the sum in the exponents, or difference in the exponents, to break it up using the properties. So this part is just a number there. I can rewrite this as 1 over 3 to the 7 times 3 to the 4th to the x. So I've taken my weird looking exponential function and I've rewritten it in terms of, well, not in terms, but into the form I have for the general up there. I've got c times a to the power of x. But because we can do things like that, we never really care about having a general form of an exponential function, because the form is relatively unimportant, because a lot of times we want to manipulate it just to make the problem easier to solve when we have a problem. Now, one of the nice things about exponential functions, and also the logarithmic functions, is they all kind of look the same. So let's say I've got f of x equal to a to the x, and I'm going to fix a to be greater than 1. So an example would be like what we started with, f of x equals 3 to the x. This graph will always take the form flat here, and then it shoots up this way. Crazy. Now, if I make the number smaller than 1, so let's see, 0 less than a less than 1, then this is a number like g of x equal to 1/2 to the power of x, which I can rewrite as, let's see, 2 to the minus 1 to the x, which is 2 to the minus x. So now I've got a positive base, but a negative in my exponent. And what that does, if you remember transformations, if I put a negative on the x, that is a reflection across the y-axis. So what I actually get when I have small numbers as my base is I have a downward moving exponential function. And then finally, if I let a be equal to 1, then what do you think I'm going to get? I get 1 to a power, and I always get 1 every time. So that's actually just a constant function if I let a be equal to 1. Now, I mentioned this before, but we want the base to be a positive number because there are very difficult to solve or difficult to communicate, rather, domain problems if I say I have -3 to the power of x. It gets very scary to look at the negative x values. So we avoid that just by saying, as a rule, the base must be a positive number. And the same thing for logarithms. When we're talking about functions there, the base must be a positive number. Now, one of the reasons we like exponential functions for the future is that their derivatives are very easy for calculus. So before we go into something special, we'll just make a note. The domain of f of x equal to a to the x is all real numbers. So minus infinity to infinity. As long as I have a positive base, I can plug in any number I want, and I will be able to find that answer. It's relatively easy if I've got fractional exponents or whatever, but finding the actual value of an exponential function at scarier numbers, irrational ones like square root of 2 or pi, they require us to do limits actually to evaluate, and we really don't want to do those. So we'll just stick to calculators. And the range of the basic exponential function is always 0 to infinity. See, if I have a positive base for an exponent, I should make a note here. A is greater than 1. So this is our basic exponential function. For the numbers smaller than 1, we can flip it around. It's just really important that we don't have negative numbers for the base. So there is a very special exponential function, f of x equal to e to the x. You might call this the natural exponential function, and we use this function for basically any problem that's involving nature, more or less. But also just as a matter of convenience because it matches up with another nice logarithm. So in the future, this function is our favorite because the derivative of e to the x is actually itself. Oops. Which is probably the primary reason we use it for natural things, is because its derivative is itself. And so that simplifies the process in a lot of problems. So E is equal to 2.71882818284590, and some other numbers after that, forever. It's an irrational number, transcendental number, whatever. It's kind of like pi, actually, except it doesn't go with any shapes or anything. And in fact, E is the result of a limit from calculus. We write limit as x goes to infinity of 1 plus 1 over x to the power of x. So what this number says is if I take this expression and I evaluate it at larger and larger numbers for forever, then I'm going to get an answer which is closer and closer to the true value of E. And if you look in the book, page 277, you'll see a chart where they do exactly that. They just plug in very large numbers for n, or x, whichever. It's just a letter. They get numbers as a result which are closer and closer to this magical number e. And this magical number e is the only function whose derivative is itself. So we're going to be using it for a lot of functions, although it's not necessary to be the only letter that's used. This is all of the basic information we need out of this section. Really understand the shapes of the graphs. I'm not going to force you to graph these significantly by hand, because you can identify or match up with a graph just by testing 2 points with an exponential function. And it's only important to understand the general shape of the graph. If I have a base which is bigger than 1, it's going to be going up. If I have a base which is smaller than 1, it's going to be going down, as long as my exponent doesn't have any negatives attached to it. Plus, we can just use calculators to graph things these days here. We'll worry about actually graphing things when it comes to chapters in calculus. As well, understanding the parts and the properties of exponents. We're going to combine this with the next 2 sections next week in order to solve problems involving exponents and logarithms.